right. How's everyone doing? All right. Hi. Hello. 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 So I know because I saw after lecture the other day that people are commenting on YouTube. I do not know how to access the live comments on YouTube, nor would I want to. So anything like whether in the room or if you're watching remotely, which is fine. It's a little bit lonely here without you, but it's okay. So just go on Discord, ESC180 lecture. I will ask, I created 2 channels for the trolls. So the trolls go there. This is just for the lecture. Yes. I think so. If it's not, is the Discord link not working for someone? For you, for example? Okay. Okay, let me generate a new one just right now. There's people coming in anyways. Okay, I am inviting you, and if you go to slide 14, there will be a fresh Discord link right there. All right, with my personal compliments. Okay, all right. So last time we stopped at trying to figure out how many perfect squares there are that are smaller or equal to n. So we did it kind of the silly way. And I'll recap how we did it, and then we'll try to do it the smart way or the smarter way. So essentially what we did last time is, sorry, quiet down, please. Thank you. So essentially what we did last time is we said, okay, so let's try I, 0 and 1 and 2 and so on up to n. And then let's ask, is I equal to square root of n? And if yes, that means that specifically because it's equal to I squared. Right? And then if you remember, we also had a not amazing way of computing square root of computing square root, but kind of apart from that. So let's do it a slightly different way. So essentially, I'll do square root the normal way, but I'll still just try every possible square root. So I'll say for I in range from 0 and up to n plus 1. And then I'll say if I squared is equal to n, well, sorry, this is perfect square. And if I is equal to n, then I'll return true. If I tried every possible square root and I didn't find that n is equal to I squared for any I, then I'll return false. So this is this. With me so far? So sorry, I moved things around a little bit. So what I'm doing is I'm saying n is a perfect square if I can find an I such that I squared is equal to n. And then I go through every possible I, And if I find that I squared is equal to n, then I found the square root of n, and I found that the square root of n is an integer equal to I, so I return true. If I tried every possible integer square root, so here I'm trying every possible integer square root, and I didn't return true, that means that there is no possibility of there being an integer square root of n that's between 0 and n, so I return false. Yes?
Like for iron range, whatever, you would say n space plus space 1. When you're writing like that, do you like does Python care if the space is there?
Right. So the question was whether I would write it like this, right? And the answer is Python doesn't care. It's a little bit a matter of personal style, how you write it. The reason I chose to write it like this here is that this is the more usual thing that you see, at least kind of for my intuition, this looks a little bit nicer. At the same time, I do write it with spaces like this when there is an assignment. It's a matter of personal style. I think most people would write it the way I did, because if you add a bunch of spaces here, it kind of looks like too many spaces, but personal style as well. Yes.
So basically, if I is equal to the square root of n, and because I is an integer, n is a perfect square.
Yes. If I squared is equal to n, then that must mean that n is a perfect square, because I is an integer, I squared is equal to n. The definition of a perfect square is that the square root is an integer. Okay, so I kind of alluded to the idea that what I'm basically doing is computing the square root of n. So let's write it out. So return the square root of n. Assume that square root of n is an integer. So you saw those kinds of things in the project as well, where you are allowed, if you like, to just write a comment and just say, the comment says that I'm assuming that the square root of n is an integer. I'm not responsible for anything that happens if the square root of n is not an integer. Similarly to how in the project, you are assuming that activity is a string. You're not responsible for what happens if activity is not one of the pre-specified strings. Of course, Python doesn't know it, it's English, but sometimes it's appropriate to just say, it's up to the user of the function to say, to use the function as directed. And in this case, you're not supposed to be using integer square root unless you know that the square root of n is an integer. So how do we do it? Well, the idea is I'll just do exactly that, except I'll return I instead of true. Right? So I'm just copying and pasting this. And I'll say return I. So it tries every possible I, and assuming that there is an answer, it will return. It might be that there is no answer, in which case the comment says that I'm not responsible for what happens. I could say I'll return -1 or something, just because. That might not be great, because if I return -1 and the user who gets the answer from a function tries to treat it as if it's the actual square root of n, that would be bad. But there are no good choices right now with the mechanisms that we have in Python. Yeah. I could return none. In fact, what will happen if I don't return anything and I don't return -1 is none would be returned by default anyway. Yes. I could return false. Again, you could specify what you want to do, and anything that you specify would be fine as long as you specify. what I would probably do with the tools that we have right now in Python is either none or something like error in quotes, in which case, if I try to do math with integer square root, did not yet finish this. So if I try to do math with this, so let's do 5. 5 does not have an integer square root, so that returns an error. So if I try to do square root of 5 plus 1, that will say that's an error because I tried to add error in quotes and 1, so that doesn't make sense. So that's a decent design because that means that I will not be able to use the error output as if it's a number. So I'll know that something went wrong at some point, which is better than something going wrong silently and me not knowing about it. Make sense? Questions so far? So let's do this now using kind of the slightly smarter design. So I'll say if so essentially what I want to do is I want to compute the square root of n. And here it would be, if it's not an error, then n is a perfect square. So this would be return true. Else, I would say return false. Does anyone see a way to streamline this? So there is a one-liner that's equivalent to what I did here. Yes. Exactly. So if I'm saying if this is true, return true. If this is not true, then return false. That's the same as saying return the condition on line 24. So what I'll do is I'll comment this out. And I'll just return integer square root n is not equal to error. So that's basically the same algorithm, except I'm explicitly computing the square root by trying every possible answer. So I would say this is a little bit nicer because you're kind of naming the concept here. You're naming the concept of I'm trying to compute the integer square root, and which is the same as here. And then you're saying, well, I'm checking if the number is a perfect square by computing a square root and checking that it's an integer. So, all right. So here, what I'm now able to do, and this is what we've done last time, and then we'll move on. I'll say for j in range 0 to n plus 1. So this would be the number of perfect squares squares usually spelled like this. And what I'll say here is check if j is a perfect square. If it is, increment the count. And I could use either one of my is perfect squares. Initially, count would be 0. Or scroll down here. And here I'll return the count. Does that make sense? Questions? So that was from last time. Let me do just one more variation on is perfect square, which makes more sense. What would you do if you wanted to use this, but make it faster? Ideas? So here's the problem. Here's the problem. Imagine that n is like 1,000,000. And the way I'm trying to compute square root of 1,000,000 is I'm saying is 0 the square root of 1,000,000, is 1 the square root of 1,000,000, is 2 the square root of 1,000,000, is 3 the square. I was going to go until 5, but you get the idea. So that's probably not the best way to compute the square root. So Python has a built-in square root, which we've used for solving the quadratic equation and stuff. Right, so why don't we just do that? So what can I do? I can compute the square root of n. That's the square root of n. And then it might be a fraction, it might not be a fraction. How do I know? Well, I can square it back. But I have to first bring it down to the nearest integer. So you can compute the floor of a number using, for example, math.floor. This just takes away the fractional part. So this number is square root of n rounded down, squared again. If the rounding down doesn't do anything, then that's just n. If the rounding down does take away the fractional part, then this is not n, this is a little bit smaller. Does that make sense? Questions about it? Who is not with me? Okay, so let's just do a numerical example. So 25 to the power of 0.5 is equal to 5. On the other hand, 26 to the power of 0.5 is equal to 5 point something. We can see exactly what it is. Compute it. So 5.099, stuff like that. Now, floor of 25 to the power of 0.5 is 5 again, because the floor of 5 is just 5. The floor of 26 to the power of 0.5 is also 5, because you're just taking away the fractional part. If the floor doesn't make a difference, then squaring the number back is going to get me the original number n. Yes? Objections? Yes.
You just finish this off by saying equals n.
Yeah. So we just say, is this equal to n? Question on this? How's Discord doing? Someone tagged me. Oh, I have a private message. Amazing. Okay. Oh, that's probably a friend request. Okay, I'll be your friend, but later. Okay. Okay, questions about this? All right. So that's a little bit faster. We won't get into how the square root is computed exactly, but we will later have something that would approximate the square root a lot faster than just trying every possible number. I wanted to get back to the original question of, this is still kind of silly. I'm computing the square root of n, and my goal eventually is to just know how many perfect squares there are that is smaller than n. So let's think about it like that. So perfect squares are 0 and 1 and 4 and 9 and 25 and 36 and so on. And what I'm asking is how many perfect squares there are that are small or equal than n. So what's a really fast way that doesn't involve going through a lot of possibilities to find this out? Any ideas? There's not a formula or anything, but yeah. Again, kind of computing the square root is kind of difficult. So let's say I don't want to compute the square root, and I don't want to do the square root in a rounded bot way either. Is there other ideas? Yeah.
Just use a for loop and say, like, say if I squared is less than 2n.
Yeah, exactly. So instead of going back, instead of saying, what's the square root of this? What we can do is we can just say, okay, let's count up from 0 to 1 to 4 to 9 and so on, up until we reach over n, at which point we know that we've gotten all the possible perfect squares. So let's write this. So that's the same thing, but faster. So the idea, again, is keep computing the next perfect square, count how many iterations it took. So that is a while loop, because the whole idea is I don't know how many squares there are up until n, and I'm just going to keep counting up. I'll start with 0, then 1, then 4, then 9, then 25, and so on. And just like when we were computing log 10, I don't know ahead of time how many times it's going to take. That's what I'm asking. So we'll still have a count. And we'll have a current square, which I'll initially set to something that's definitely smaller than n. So let's say -1. And we'll have an I that's equal to -1. And I'll say, while current square is smaller or equal than n, that's smaller than n if it's more equal, sorry. So we'll figure it out when we're there. What I'm going to do is I'm going to increase I, and I'm going to make current square be equal to I squared. And I'm going to make count be 1. So here I'm being a little bit finicky because I and count are almost the same thing. But in the design, I'll first do it like this, and then I'll fix it up. So I'm trying to show you the process here. So does this make sense as a concept? Current square is going to be 0, 1, 4, 9, 25, and so on. And we keep going while current square is smaller or equal than n. And the question is, how many times will we keep going? So in this kind of situation, especially if I'm at the computer, what I'll do is I'll just start with a draft like this, and then I'll try running it. And I'll see whether I have what's called an off by one error, one way or the other, where maybe I overcounted by one or undercounted by one. We'll say n perfect squares fast. And I'll pick something small. So for example, 5. So the answer here is going to be 3. So I'll put a breakpoint here. And I'll step in. So right now, count is 0. I want to return 3. So I is now about to become 0. I'm computing current square. Current square is 0. And I've counted the fact that I've computed 0 squared. And now count is 1. Make sense? So is 0 smaller or equal than 5? Yes. But do I want to keep going? Also yes, because I want to count off 0 and then 1 and then 4. So I'll just try the next I. I is now 1. Current square is now 1. And I've computed 1 as well. So count has gone up to 2. Count equals to 2 means that I've done 0 and I've done 1. What I'm going to do next is compute 4. So again, I've now computed 4 as well. So current square is 4. I did it 3 times, count is 3. Is current square smaller or equal than n? Yes, current square is 4. It's smaller or equal than 5. So I'll do it one more time. And now count became incremented by 1 again. So current square is now 9, which is not small or equal than 5. So I'm here, and what I'm about to return is 4. The reason I'm about to return 4 is I computed 0, and I computed 1, and I computed 4, and I computed 9. With 9, I overshot. Count, by the logic now we understand, is the number of times we computed I squared. The problem is the number of times that we computed I squared is actually 1 more than what we need, because we don't know that we overshot until we did actually overshoot. Does that make sense? So what's a 2-character fix to this code? There's several possible ones, but I'm looking at line 62. What do I want to return? Yes. Count -1. That's exactly right. So if I say count -1, what I'm doing is I'm saying I tried to compute a square until I overshot n. So I computed one more square than I needed to. So I'll return count -1. Now, another issue that I mentioned is that actually count and I are kind of almost the same thing. It's just that count is 0 and I is smaller than count by 1, because it starts out as -1 and I'm incrementing I by 1 and I'm also incrementing count by 1. So that's kind of a waste. So the other thing I could do is say return I and just forget about the count completely. So here I could make a comment and say I is just I, but it's also the number of times we computed square. Make sense? Initially, it doesn't really make sense, except if you say, well, we computed 0 squares, and then 0 minus 1 is -1. And then we compute a square, and we also increment it. Yeah.
Like, what if it was something else?
Yeah, I was thinking ahead. So I wanted to, so because in the while loop, you have to first check something, and that something until you have computed the square doesn't really make sense. What I chose to do is I chose to make current square initially not make sense so that the condition is definitely correct, assuming that n is a non-negative integer. And then it starts making sense right away after I becomes greater by 1 and current square becomes 0 squared initially. Make sense? So the other thing that we discussed last time as well is you could also do the computation for current square the first time outside the while loop. In the same way that you could take the input outside the while loop in Monday's example, I prefer not to replicate code. So that is ugly in its own way because I'm saying I -1, current square is -1, which is a fake square. But I think it's preferable to replicating the operation of squaring both inside the while loop and outside the while loop. Is that making sense? It's kind of a repeat of Monday. Let's do it on paper as well. So I could do an alternative design, which I'll comment out. So I'm not even going to run it, but just to show you, I don't think it's a good idea. So that's why it's a comment. I'll say I is equal to 0, and then I'll say current square is I squared. And then because now I'm computing current squared initially, I will be returning I +1 rather than I, because if I is 0 and n is 0, I want to return 1. again, you would logic it out in the same way that they logic things out when I was doing the iteration before. I don't think it's as good, so I'm not going to do it in lecture, but you can try it. Does that make sense as an idea? I'm not going to get into the details because we spent too much on this. Questions? Does anyone really want me to do this? Please don't say yes. Okay. All right. 6 notifications. Oh, new friends. Okay, great. Okay. Yeah, I wasn't trying to get new friends on Discord. That's not one of my goals in life, but I'm happy to be your friend. Okay. So here is another way of thinking about what we were talking about 15 minutes ago. I could define a function, I'll name it property, which could be any property of n. For example, the property could be that n is a perfect square, but it could also be that n is an odd number, or it could be that n is equal to 42. I could say anything in that return. And for example, it could be like a prime number. So I could take 11. So I could take this kind of thing and just check any property that I want. So I could say, for example, but I could also change this code to is prime, the function that we wrote before, and property would still work the same way. Does that make sense? So for any question of the format, how many numbers up to and including n with a given property, what they could do is they could just change the function property, and n property would be exactly the same. Does that make sense? Yeah.
Instead of just writing like the property function definition twice, could you just like comment one with return?
So there are different ways of doing it that are more elegant that we'll get to later, is the answer. Yes. Oh, it would in the same way. So I just started the file from scratch, which also doesn't have is perfect square as a function. So in the same way that we wrote the function as prime, we would include it somewhere. Yeah, the answer is it wouldn't know what the function as prime is unless you tell it. Other questions? All right. So as you progress, this is not the most elegant thing that you could do, but this is getting to kind of a more elegant way of writing things, which is one of the things that we'd be looking for in this course as well, although mostly we just want things that work. So, okay. I'm gonna skip this slide with your permission. There is actually without your permission as well. There is a lab question today and tomorrow, depending on when you're doing the lab, which is kind of similar to this. I will do the lab, and if people ask for this question as well in tomorrow's lab session, just to remind you, Thursday, 6 p.m., UC 244 is the lab solution session, also on YouTube, also posted to the course webpage after it's recorded. So, okay, let's talk about something lighter for a while, just object types. This is stuff that you've already kind of seen, but I'm going to do it in a more formal way. So Python has different types of what's called an object. So one type of object is a string. So in Python, this would be denoted as str. You've seen strings. Another type is a float. Another type is an int. Another type is actually a function. So if I ask for the type of 42, Python will say int. If I'll ask for type of ANSI, Python will say str. If I ask what the type of print is, Python will say it's a function. This goes back to something that we've seen in Python Tutor and something that you see in the workspace all the time. When you define a function, it's actually another type of object in the same way that an integer is an object and a string is an object. So you see it all the time in the workspace. So it's a good thing to know. We'll also see later a way to use the fact that a function is just another type of object that you basically store in a variable. So that is what that looks like. You'll notice that function and built-in function like print are technically different, but those are not details that we're going to get into. Does that make sense? So you can convert between different values in Python. The way you convert is you give the name of the type, so int or float or str, and then you use it as a function. It's not a function, but you use it as a function, it computes a value. You can, for example, convert 3.65 to an integer by saying int of x. The way floats are converted to integers is by truncating. So the fractional parts just goes away. You can think about it as rounding down. For negatives, it's for negatives, it's actually rounding up, because really what you're doing is you're removing the fractional part. Some things do not convert. So you cannot, for example, say int of the string 3.78, because 3.78 is not an integer. So sometimes, and those are rules that I'm telling you about right now, sometimes Python says, okay, x is a float, it's not exactly an integer, it has a fractional part, but the rule is I'm truncating, and that's the converted value of the integer. Sometimes Python is going to say, I'm not going to convert the string 3.78 to an integer for you, because you're probably wrong about what you think it is, because it doesn't look like an integer. How do you know? You don't. Those are rules. I just told you what they are. If you do want to convert a 3.78 string to an integer, you can. You just have to first convert it to a float, and then you are allowed to convert a float, 3.78, to an integer. So the value of that would be 3. Does that make sense? It shouldn't really. Those are just rules that I told you about. You don't logic them out. This is just what they are. There's not very many of them. This is everything that you need to know for this course. So we now are able to combine the input function and converting the types in order to make a calculator that's a little bit more than what we've done so far. So what I want to do is I want to say input an operation. And then I want to input the left-hand side operand. So operand is the thing that the operation works on. So 1 plus 2. Plus is operation. 1 and 2 are LHS and RHS operands. So that is what I want to do. Does that make sense? So let's do it. Let's say operation, and I'll ask the user for the operation. The operand, I'll ask for the LHS. Give me 2 minutes, please. And if I do this, so let me just run it very quickly. So let's say that I say that the operation is plus, and then I say that the LHS is 34.5. LHS operand is going to be the string 34.5. If I ask for the type, it'll say str. If I want to add 34.5 and another number, it has to be converted to a float. So that's what I'll do is I'll convert it to a float. I'll do the same thing with RHS operand. And now that I have the left-hand side and the right-hand side operand, and I know what the operation is, I'll perform the operation. So I'll call this function artsmath. Technically the Department of Mathematics and Arts and Science, but whatever. And I'll say if operation is plus, I'll return LHS plus RHS. And I get to do that because LHS is a float and RHS is a float. And then else, if it's minus, I'll return minus. And else I'll return, well, I'll print an error message. Okay, and I'll return an error. Okay. So let me run this at the time here. So here I'm assigning the value to operation. Let's say minus. Here I'll say like 34 and I'll say 4. I didn't print it, but that would return 34 minus 4. Whereas if I say times, that would be artsy, can do complicated math error. Okay, thanks for bearing with me. I will see you on Friday. Bye.